Okay, um, before we go on to the two types of analysis, as noted earlier, there are two methods that can be applied to analyze the voltage divider configuration. The reason for the choice of names for this configuration will be obvious in the analysis to follow. The first to be demonstrated is the exact method, which can be applied to any voltage divider configuration. The second is referred to as the approximate method and can be applied only if specific conditions are satisfied. The approximate approach permits a more direct analysis with a savings in time and energy. It is also particularly helpful in the design mode to be described in a later section. So all in all, the approximate approach can be applied to the majority of situations and therefore should be examined with the same interest as the exact method. Alright, okay. So now we go on to the exact analysis. So the first step is to redraw the circuit. Alright, this circuit comes from the voltage divider circuit. So after you have redrawn the circuit, you need to find the Thevenin equivalent circuit. So in order to find Thevenin equivalent circuit, there are two things that you need to bear in mind. You need to find, the first one is RTH, or Thevenin resistant equivalence, Thevenin resistance, and the other one is VTH, or Thevenin voltage. Okay, for you to find RTH, VCC will be short circuit. VCC will be yes, short circuit. So from here you can see, so R2 will be parallel with R1. So that is why you will get this equation, RTH equals to R1 parallel with R2. So remember, if you want to find RTH, you need to short circuit VCC. Alright, and the other one, VTH. If you want to find the value of VTH, the equation, and also the equation, you need to find at resistor R2, voltage at resistor R2. So in order to find voltage at resistor R2 by using voltage divider rule, you will get R2 multiplied by VCC over R1 plus R2. This is actually the voltage divider rule. Okay, so step 3 is to replace Thevenin equivalent circuit. So after you have find RTH and also VTH, you have to redraw this circuit, okay, the Thevenin equivalent circuit, and put the value of RTH and also VTH. And then step 4, apply KVL to determine IB and VCE. So from this circuit, from the Thevenin equivalent circuit, you can find IB by using the loop equation here. Okay, that is it depends on you whether you want the first polarity to be the sign, or you want the current leaving the terminal to be the sign. It is up to you. So from here you can get this equation. Okay, and also VCE, you can get the equation for VCE by looking at the output loop, this is the input loop and this is the output loop. So okay, but okay, it's okay, let me explain how to get this equation. Okay, for IB, starting from VTH, if I choose the sign to be negative, so it will be negative VTH. IB RB should be RB, but here you have substitute into RTH, so IB RTH, and then plus IB RTH, and then plus VBE, and then plus IERE equals to 0. So move all the notation to the other side and remain IB. You will get IB equals to VTH minus VBE over RTH plus in bracket beta plus 1 multiplied by RE. Alright, so VCE is actually comes from the output loop over here. So it is better if we look at the voltage divider circuit over here. So VCE actually comes from this equation, VCC plus ICRC plus VCE and then plus IERE equals to 0. So from there, remain VCE, and other than that, move to the other side. So you will get VCE equals to VCC minus IC in bracket RC plus RE. Alright, that is the exact analysis. Now we move on to the next slide. So this is the example for exact analysis. Actually, this is the one of the exercise. You have to determine VCE and IC from this circuit. So you guys need to do the exercise. You can just follow the steps from the previous slide. Alright, the second analysis is approximate analysis. Used for circuit that have a very small IB due to large resistance between base and ground. So if R in is greater than or equal to R2, what will happen is that IB will be less than I2. So I1 will be approximately to I2. Okay, so if you want to do approximate analysis, I advise you, the first thing you need to do is to test beta RE, is it greater than or equal to 10R2. Okay, the reason we test this because we want to see the resistance at RE and also the resistance at R2, which has the higher resistance. So if it is satisfied, means that if beta RE is greater than or equal to 10R2, then you can use the approximate analysis. But if beta RE is less than 10R2, means that you have to do the exact analysis. So in this case, if it is satisfied, means beta RE is greater than or equal to 10R2. Okay, so you can use the approximate analysis. So in the approximate analysis, this is the circuit. Okay, so from the voltage divider circuit, it will become like this. Alright, so here as you can see, this point here is VB. So the equation VB equals to R2 times multiplied by VCC over R1 plus R2 comes from this voltage divider rule, that is the voltage across R2. So how to get voltage across R2? By using VDR, you will get R2 multiplied by the source, which is VCC, and divided with R1 plus R2. So this is actually voltage divider rule. Okay, so VE is actually the voltage that comes from this loop. Okay, this loop over here. So once you have VB over here, so the voltage VB will be the input for this loop over here. Okay, so the equation will become VB over here, and then VBE, and also VE. IE is actually VE. Okay, so VE is this at this point. So IE multiplied by RE will get VE over here. So the loop equation, if you choose the sign to be minus, is the first sign that you want to do. So the equation will be minus VB, and then plus VBE, and then plus IERE, or you can just plus VE. So from there you will get this equation. Alright, so just remain VE, and all the notation move to the other side. You will get VE equals to VB minus VBE. So if you want to find IE, you can just do the equation IE equals to VE over RE, since IE is the current that flow through RE. Alright, so that is the input loop. So now we look at the output loop. So from the output loop, the equation will be minus VCC plus ICRC plus VCE, and then plus IERE. So remain VCE, and all the others just move to the other side. You will get VCE equal to VCC minus ICRC minus IERE. Since we know that IE is approximately to IC, so by substituting the IE equals to IC, so you will get VCE equals to VCC minus IC in bracket RC plus RE. This is actually after you have simplified the equation. You will get RC plus RE multiplied by IC. Alright, now we go on to the next slide. Okay, this is the example of approximation analysis. So this is the question that is for you guys to determine the value of VCE and also IC. Alright. Okay, now we look at the DC bias with voltage feedback. Okay, this is a feedback circuit. Okay, DC bias feedback. Another way to improve the stability of a bias circuit is to add a feedback path from collector to base. So this is the feedback circuit. As you can see here, RB is your feedback circuit. In this bias circuit, the Q point is only slightly dependent on the transistor beta. So the Q point will be slightly dependent on the value of beta. Alright, now we go on to the analysis of DC bias voltage feedback. Okay, DC bias with voltage feedback. So the first thing you need to do is to find the equation from the input loop. So from here, from the input loop, the equation will be VCC minus I prime C RC minus IB RB minus VBE minus IE RE equals to 0. Okay, I prime C is actually the current that flow through RC. There will be two current I see here. As you can see in this figure, I prime C is equal to IC plus IB. Okay, I prime C is equal to IC plus IB. Alright, so we look back at the equation where IB is less than or equal to IC. So approximately I prime C is equal to IC plus IB, and it is approximately to IC. Okay, since IB is less than IC, so we can just do the approximation where I prime C equals to IC, and also IC, since IC is approximately to IE, so from here we can substitute the notation of IC into the equation here, IE. So knowing IC equals to beta IB and IE approximately to IC, the loop equation becomes VCC minus beta, I think this is beta IB, RC, and then minus IB RB minus VBE minus beta IB RE equals to 0. So I think you guys need to do some correction over here. This is actually VCC minus beta IB RC minus IB RB minus VBE minus beta IB RE equals to 0. So solving for IB, you will get IB equals to VCC minus VBE over RB plus beta in bracket RC plus RE. Okay, so we move on to the next slide. Okay, this is the output loop. So as you can see from the output loop, the equation that you can get is minus VCC plus ICRC plus VCE plus IERE equals to 0. Alright, so remember that this is actually I prime C, but I prime C is approximately to IC, so you just need to substitute IC into the equation. So since I prime C approximately to IC, SIB equals to 0 and IC equals to beta IB, so the equation becomes IC in bracket RC plus RE plus VCE minus VCC equal to 0. So solving for VCE, remain VCE and all the others move to the other side. You will get VCE equals to VCC minus IC multiplied by in bracket RC plus RE. So that is the DC bias voltage feedback analysis. So this is the example of voltage feedback, DC bias voltage feedback. You guys can determine the value of IB and VCE. Okay. Remember, during DC analysis, all capacitor must be open circuit. So when this capacitor is open circuit, what will happen? The current will move like this. Okay. So there will be two current over here, IC and IB. So during the input loop equation analysis, so you just make sure that the current will move through 110 kilo ohm and 91 kilo ohm. Okay. So this is the miscellaneous bias configuration. This is the collector feedback. So you can try to determine ICQ, VCEQ, VB, VC, VE, and also VBC. This is the miscellaneous bias configuration for common collector. So you guys can determine VCEQ and IE. And then this is the miscellaneous bias configuration for common base. So you guys can determine VCB, IB, and also VCE. Okay. Before I move on to the other slide, I would like to explain a little bit on common base configuration. So if you look at these notes here, this is a common base configuration. So you can see here the base for the transistor is connected to the ground over here. So this will be the input loop and this will be the output loop over here. Okay. Alright. Applying Kirchhoff voltage law will result in minus VEE plus IERE plus VBE equals to 0. So this loop equation comes from by looking at this figure over here. As you can see, by looking at this loop, you will get this equation. So remain IE and the other move to the other side, you will get IE equals to VEE minus VBE over RE. So applying Kirchhoff voltage law to the entire outside parameter of the network, as you can see in figure 4.51 over here, so KVL will be applied to the output loop over here. So the equation, the result equation will be minus VEE plus IERE plus VCE plus ICRC minus VCC equals to 0. And solving for VCE, you will get VCE equals to VEE plus VCC minus IERE minus ICRC. Since IE is approximately to IC, now the equation becomes VCE equals to VEE plus VCC minus IE in bracket RC plus RE. So the voltage VCB is the voltage from collector to base. Of figure 4.51 here can be found by applying Kirchhoff voltage law to the output loop of figure 4.51. So from here you will obtain VCB plus ICRC minus VCC equals to 0. Okay. As you can see here, this is the equation. Okay. VCB is here. ICRC is here. So you will get VCB plus ICRC minus VCC equals to 0. Alright. Using IC approximately to IE, then you will get VCB equals to VCC minus ICRC. So that is the a little bit extra note for the common base configuration. So now we look back at the notes, lecture notes. So that is the analysis for common base. So now we look at the next slide, which is load line and maximum output voltage. Okay, so this is the DC load line. Sorry. Okay, so this is the DC load line over here, and this is the AC load line. For DC load line, ICQ, here ICQ and VCEQ you can find in the circuit during DC analysis. Okay, ICQ and VCEQ you can find the value during DC analysis. From KVL at output circuit, you can find IC saturation. That is when VCE equals to 0. Okay, after you have find the equation for VCE, if you put VCE equals to 0, then you can get the IC set. Same goes to IC. When you have find the equation for IB, after you have substitute, and then you get IC equals to what? After you put IC equals to 0, then you can get VCE at cutoff. Okay. Alright. So V out DC is equal to 2 VCEQ. That is referring to the DC load line. For AC load line, VCE prime equals to VCE cutoff or loss. So loss equals to ICQ RC, where RC is bypass resistor at output during AC analysis. V out max AC equals to 2 in bracket VCE cutoff minus loss minus VCEQ, and this is equal to 2 VCE cutoff minus VCE prime. The AC analysis, I will touch these notes on the next lecture. So lastly, maximum peak to peak output voltage V out max equals to V out max DC, or V out max AC is whichever is smaller. So I guess that is all for today's lecture. This is the exercise that you guys can do in order for you to improve your analysis. So you can try to do this exercise. This is voltage divider circuit. Okay, you can try to refer to the voltage divider circuit. Minus 22 volt means that the voltage terminal is ground, and then plus sign, and then minus sign, and then go to RC and also R1 over here. So this is another exercise that you guys can try. This is also a voltage divider circuit. So that is all. Assalamualaikum and salam sejahtera. Thank you very much. Bye.